This is a pretty standard, well, what year do you learn the volume of a cone? Year 10, maybe? Yeah, okay, so this is a pretty standard question you might have faced a couple of years ago, okay? But we're interested in more than that, aren't we? We don't just want to know how big the whole thing is, and we have the tools to work out a lot more about this, right? For instance, now I am going to have to go back to some calculus stuff, okay? When you see this, this is a shorthand, isn't it? What's it shorthand for? So it's shorthand for a couple of things, actually. I mean, I suppose you could say it's the derivative of y with respect to x. That's a very, very abstract way of saying it, but it's correct, okay? Where did that idea come from, though? Think back to first principles. What do these d's, why are they d's? What do they stand for? They stand for delta, which is about a change, right? So this is about rise over run. And we did our, we did our diagram. You got some function, and you're thinking about rise over run, and you want to make this interval, right, of this width, you want to make it increasingly smaller, right? And once you get to 0, you approach the limit. That's when you get the derivative, an instantaneous sort of rate of change, okay? Or rather, an instantaneous gradient, okay? So being that, rise over run just means how much y changes in proportion to, that's what a fraction is, right? It's a proportion, that's why they're called rational numbers, ratios, right? In proportion to how much x changes. Okay, now, you told me, right, or at least I tried, that in here we have some information about two things that change in relation to each other, right? There's a few things actually, right? What might be a good place to start? Where do we have the most information? I'm thinking it's probably the pouring rate. I think that's what we know the most about, okay? Now, to be honest, I have no idea how long it took me to put that in. Though, I suppose we could make a guess. How long did it take for me to pour the whole thing? 20 seconds? About 20 seconds, okay? So, if I know that this is the volume, roughly, okay, and it took me about 20 seconds to pour the whole thing, okay, what might be an appropriate number? Like, in terms of centimeters cubed, that's a pouring rate, isn't it, right? Per second. How many cubic centimeters was I pouring in every second, roughly? Divided by 20, right? About 180, right? I suppose we're a bit off because that 3619, right? But it's all sort of approximations. Let's call it 180. 180 cubic centimeters per second. Is that consistent? Does that sound about right? How much is 180 cubic centimeters? It's about 180 mils. 180 mils. How big's a cup? Like a cup of water? It's about 250, isn't it? So like 2/3 of a cup. Does that sound about right? Yeah. Maybe. I mean, we're picturing a bigger cone, aren't we? So yeah, I think we're in the right ballpark. Okay. So let's call this how much the volume changed of water in there, right? Over how much what? Now the thing is, the rate tells you, doesn't it? The rate itself tells you. Here you have a volume, right? And here you have a time. Cubic centimeters, seconds, right? So the units tell you what kind of a rate of change you have. So this is dV on dt. Is that okay? Can we accept that? Okay, this is interesting, right? Now, be careful. I'm going to rub off some stuff off the board in a second because I don't think it'll be useful to us anymore, and in fact it'll actually be confusing. What is dV on dt? Or rather, what's V in this case? Be careful. Because it's not the volume of the cone, is it? Because the volume of the cone is this. How does this change with respect to time? Answer, it doesn't. It's always that volume, isn't it? It's been that volume the whole time I've been talking and it hasn't changed, right? So this volume, this V, is talking about the whole thing. But that's not what this is, right? What's this V? This is the volume of the water that's actually in there, and that's changing. Does that make sense? Be careful of these kinds of things. So therefore, I'm going to get rid of all of this because it's not going to be useful to us afterwards, right? And I better, when I'm talking about letters here, I better say what they are, right? So let's say this. Let V equal, and I'll call it the volume of water that's in there in the glass. Whoops, sorry. After, well, I'm talking about a time as well, right? So I might as well relate these to each other because apparently they are. So it's the volume of water in the glass after, I'm talking in terms of seconds, aren't I? That number of seconds. Okay, is that all right? So now I've got some variables here. I've got a rate of change, okay? But I don't yet have any related rates of change. There are some other rates of change happening in this scenario, aren't there? What kinds of other things can you see? There's height. We identified that, didn't we? Right? And we said we drew some observations about it, okay? What's the height? Now, we're interested in this. You were saying the height was changing with respect to what? Over time, right? As time passes, the height gets, well, it increases, yes? But this is a problem. Where did we get this expression from? We got it from the fact that we were making an observation over time, okay? And we know what the volume of the whole thing is, so we got a number out, okay? How will we do this? We can't quite do it the same way we did it before, can we? Okay? Because as you noticed, if I do the same thing, make the same argument, I've got a height, right? And I can say, well, 24 centimeters, right? And it took, what did we say, 20 seconds? 20 seconds? Okay. Over 20 seconds. Okay? So, you know, I say that height over that time, that's 1.2 centimeters per second. That's what it looks like I would get, but it's not. Why not? Because, as you told me before, the rate of height increase, how much this thing is, right? It slowed down, right? It started off quite quickly, didn't it? And then as it got to this top, you were like, oh, is this ever going to get to the top, right? Actually, I wasn't sure if it would get to the top. Didn't know if I had enough water. This thing here, this doesn't change. This is a constant. It's always 1.2. It's like it sort of goes up at a gradual rate and never slows down or never speeds up. So this is not dH on dt, right? So therefore, how can we get an expression for dH on dt and draw some conclusions about it? Okay. Right, we need some more information on this diagram. So we've got some concrete measurements, okay? But I want to introduce some changing measurements, okay? So if I put in this, sorry, I'm going to talk about h in a second, right? And h is something that changes. It's not 24. How do you think I should define h? Think about the way I defined v. I want h to be a changing thing, namely the height of the water in the glass after t seconds. So it corresponds to v, doesn't it? So is the height of, not the cone, but the height of the water that's in there, okay? Now, here's the thing though, because it's a cone, when I put water in, the water will also be in the shape of a cone, right? You've got similarity all the way up. So let's draw a point in time, okay? Something like this. I've got blue. Where's my blue? There you go. There's some water in there, okay? So now I can put some measurements on here, can't I? Okay, I'm calling the height of this thing here, that height there, I'm calling that h, right? Now if I want to work out the volume of the water, V, the V that I'm talking about, right? How am I going to work out the volume of this cone down here? What information do I need? If I want a volume of a cone, you told me about 5 minutes ago that the volume of a cone is 1/3 pi r squared h, right? Okay, now we're talking about our V. That's why I put it in another color, okay? This volume of water that's changing, okay? Now, I know what h is. I'm calling it h, okay? But what's the radius? Can you see why I picked the numbers that I did? What's the radius going to be? When I get to the end, whatever time, after 20 seconds, okay, my h will be 24 and my r will be 12. Yes? Because I'm finished. It's the whole thing, right? At the beginning, my height's 0 and my radius is also 0, okay? But in between there, we have a whole bunch of similar cones, don't we? They're all similar to each other because they're all in the same kind of shape, yes? So being that the relationship between these two numbers is that the radius at the top is half of the height, okay? And all of these cones as I go up will be similar, okay? What's the radius going to be? At some arbitrary point in here. Well, it's going to be half of the height, isn't it? That's what similarity means. Okay? All of the sides will always be in the same proportion. If the radius is half of the height somewhere along these, in one of these similar shapes, then the radius will always be half of the height. Okay? Good, so now I can say, what's the volume? The volume is a third pi, now what's the radius? It's h on 2. H on 2 squared times h. Let's just tidy that up a little bit. That's h squared on 4, isn't it? H squared on 4. So I'm going to get, by the looks of it, 1/12 pi h cubed. Is that okay? Is that all right? Now, if I know this, I can make some statements because V, the volume, and H, the height, are connected to each other, right? So if they're connected to each other, as the height of the water changes, the volume changes, and vice versa, right? So this equation represents a relationship that I can manipulate. Because I can do this, right? Sorry, wrong color. I can work out that, can't I? Because this is just going back to calculus stuff. There's an expression with an input and an output, right? So I can differentiate, can't I? What's the derivative? Well, it's with respect to h, so this 3 comes out the front, right? So it'll be a quarter. Pi is just a constant. And then it'll be h squared, right? Now, this is a little bit weird because we're so used to thinking in terms of x's and y's, okay? But, you know, it's just a 2 variable function dressed up in different clothes. That's all. We can do all the same rules, okay? Now, what was I after? I was after dh on dt, wasn't it? Wasn't I? How the height is changing, okay? Do you see now, I actually have enough information to work out dh on dt. Can you see it? Think back. Which piece of knowledge that you know is going to be relevant here? Let's move this other way so you can see the board. It has a name. It's called chain rule, isn't it? Think about what's happening. I have 2 derivatives here. 2 derivatives, okay? And they have all of the pieces I want. There's an h here. There's a t there. So I should be able to combine them to get a dh on dt. Yes? How am I going to do it? What's chain rule going to look like? dh on dv, because I need the dh on the top, don't I? Okay. Multiplied by dv on dt, right? Now, I almost have these, don't I? I've got my dv on dt, check, it's just a number. dh on dv, I don't quite have that. I've got its reciprocal. But no problems. I've been teaching year 7 about reciprocals recently. I think you guys can do a reciprocal. What's the reciprocal of dv on dh? It's 4 on pi h squared, isn't it? Times dv on dt. It's 4 times 18. What's that? 72? So that's 720. Now, let's stop for a moment, shall we? And observe, okay? What does this tell us? Assuming we've done everything correct, all of these sort of hold, and everything makes sense apparently. What can you observe about our wine glass and the water inside it from the maths? What does the maths tell you? This is how much the height is changing. Right? This is how much the height is changing. And this kind of function, well, what does it look like? Well, for starters, h can't equal 0 on that function, can it? Right? Why would that be? Why would that be? Because when h equals 0, when there's no water in there, how's the height increasing? Well, it's not increasing, it's not decreasing. I have no idea what it's doing. It's not doing anything, okay? So this is not defined when h equals 0, but I can draw what it looks like for the rest of it, can't I? Something like this. Be careful, by the way. What are my axes going to be? We're so used to x and y axes, we just kind of do it blindly, don't we? What are my axes going to be? Okay, so this one's going to be dh on dt, isn't it? That's what we're plotting on the vertical. And this is going to be h. So we're thinking about what happens to the rate of the height change, height increase, okay, as the height increases. Now we already established, didn't we, that it's not defined at h equals 0. Okay, so there's an asymptote there. Right? What happens as h increases? The denominator is getting bigger, so the whole number is getting smaller, isn't it? Right? So it's doing this kind of thing. Isn't it? Is that sort of accurate? Yeah. Now, by the way, I know that it looks like this and not like this at a linear rate. Can anyone tell me why it doesn't look like that? What kind of shape is this? We have language to describe this kind of thing. What is it? It's a hyperbola, isn't it? Of kinds, right? And we know hyperbolas have this sort of curved shape. And it also matches this kind of thing over here that we saw, right? So it's not just slowing down, it's slowing down at a slowing down rate. That's funny. Okay. Now, there's a problem with my graph though. There's a problem with my graph. Can anyone spot it? I want you to think about all the things we observed, right? Even the most obvious things, and what my graph is telling you. What our graph is telling us.
It keeps going up.
What have I accounted for? I've accounted for this discontinuity. Right? I've accounted for how it's decreasing, which should tell me something about this shape, right? But what's happening over here? It doesn't keep going forever, does it? Right? It stops somewhere because you thought you laughed, but it's important. It overflowed, right? So the volume of water in the glass, it has a finite limit, doesn't it? It gets to a point, namely 24. Let's just call it that. And it stops. That's all it does. 24. Okay? That's a bit weird, isn't it? We're not used to graphs like that, but guess what? Welcome to the physical world. This is what graphs do in the physical world, okay?